Hey everybody, I'm Eric. So this notebook, which I'm submitting for the AlphaXiv MoLab competition, it explores BitNet. It's a paper with a crazy claim that says you can replace every 16-bit weight in a language model with just -1, 0, or +1, and the model still works. So I built this notebook to understand why that's not crazy. I'll walk you through it using this guided tour. So here's the whole idea. On the left, there's a trained weight matrix, and on the right, every weight is crushed to 3 values. The bits near 0 are the ones that get thrown away. Killing them actually costs nothing because they weren't doing much anyways. If you open the notebook, you can click around and go to round it yourself down here. And you can actually ask what happens when I completely binarize it to 1 bit. What happens when I do to ternary or 37 level versus full precision. That was a thing that I was curious about. So I asked AI to help me build that visualization as well. So how does BitNet accomplish this? It actually accomplishes this through 2 NumPy operations, rounding and clipping. The catch, if you are trained in deep learning, is that rounding has 0 gradient, and so backprop can't learn through it. So what BitNet does is it uses a straight-through estimator, also known as STE, in which during the forward pass, we use rounded weights, but during the backward pass, we ignore the rounding. So does this actually work? I used the MoLab GPUs to train a ternary network. And the loss curves, which I'll show you here, they actually track full precision almost exactly. And the STE makes the rounding invisible to backprop. So in terms of ideas, the paper kind of stops there, but I chose to follow my curiosity a bit further. My first extension was that the paper says the ternary matches full precision, but it never really sweeps a continuous precision ladder like I had shown in the buttons above. So I trained it at 6 precisions, 3 seeds each, all on the GPU. And the curve really saturates out here at 3.17 bits. This looking like a little bit like a Pareto frontier tells us how close we are to maximum precision as well on this particular task. I then tried something that the paper doesn't address, which is what if you were to ternarize a model that was never trained for it? The idea here is you take a model, say Distill GPT-2, and then you crush the weights after the fact. And obviously it will collapse because the perplexity, in which lower is better, massively increases when you go from full precision to binary retrofitted or ternary retrofitted. And that kind of makes sense as well because the model spent its whole pre-training tuning exact magnitudes. And if you strip them, every layer's calibration with each other kind of dies out. So BitNet models have to be born ternary. But the other thing that I was curious about was, can you recover a retrofitted model? So what I did was I asked AI to help me write some code to fine tune a broken model with the straight through estimator. So you have the same ternary constraint, the optimizer can adapt, and I ran this across 3 model families, GPT-2, Qwen, and Pythia. And in every case, STE can recover the model by 1 to 2 orders of magnitude, even if it's not perfect. I wanted to see if the recovery was real in terms of language and not just a number. And so here's the same prompt, which is the future of artificial intelligence is, and then with Distill GPT, this is the full precision model. Here's the retrofitted version that just spits out a bunch of E's. And here's the STE recovered version that kind of blabbers a little bit. So it's not perfect, but it definitely feels a little bit more AI related. So all of this kind of begs the deeper question. Why 1.58-bit? It actually has something to do with how matrix vector products work. When every weight is -1, 0, or +1, a matrix vector product just need additions and subtractions. And so 1.58-bit or ternary is the smallest precision that is both accurate and free of multiplications. And that is the real prize. It actually buys you about 20 times less memory use. Okay, so these 3 values, -1, 0, and +1, they replace 32 bits, and the math no longer needs a multiplier. And as we showed in the notebook, the STE recovers what retrofitting breaks, and it does this across multiple families of models, up to a 3 billion parameter model, which I was able to try out on the RTX Pro 6000 hardware that we have in MoLab. I really enjoyed building this notebook using Marimo Pair, a bit of any widget in an earlier iteration, and some really cool wiggly stuff tools. So thanks everybody for the time and watching, and I hope you enjoyed it.